We're looking at conservation of momentum, a little bit more from our lesson yesterday. So today we'll be looking more into two-dimensional conservation of momentum problems as well as rotational conservation of momentum problems. So we'll touch a little bit on gyroscopes here at the end. They're kind of cool to look at. And before that, we will get to some problems involving some calculations with conservation of momentum. But before we get going, as usual, we have our review type bell ringer question. So suppose a 60 kilogram person is traveling in a car that's traveling 26 meters per second and comes to a sudden stop in 0.2 seconds and hits the wall. So hitting the wall, final velocity is going to be 0 meters per second. What is the impulse felt by the person and what is the force felt by the person? And then we're going to take that force and compare it to how massive an object could be. So we're going to use weight. So if we just use force equals mass times gravity, we'll just use the weight of an object to figure out what that mass would be comparatively. So let's look at impulse. So remember, impulse, we just use the letter J, and that is force times time. And this, force times time, is equal to the change in momentum. So we usually start with this, and then we can kind of pull some other pieces out from this if you wanted to find a force or a time. Okay, so let's find our change in momentum here. So remember, momentum is just mass times velocity. If we had an initial momentum, that would be mass times initial velocity. So we can do that one here. So we have a 60 kilogram person, and our initial velocity is 26 meters per second. So we can take those two and multiply them out, and we'll get 1,560 kilograms times meters per second. So that's my initial momentum of the person sitting in the car. So final momentum, that would be after the person hits the wall. That's going to be mass times final velocity, which the mass is 60 kilograms. And we probably don't need to do this work, but we'll just show it anyways. And the velocity would be 0 meters per second, which would give us a final momentum of 0 kilograms times meters per second. Okay, so let's do impulse first. So impulse is going to be F delta T, or J, and that's going to be equal to the change in momentum. So we're just going to say J equals change in momentum, and that's final. So that's 0 kilograms times meters per second minus initial, 1,560 kilograms times meters per second. And we'll end up just getting this, the negative 1,560 meters per second, right? 0 minus that would give me a negative 1,560. So now I can take this, which is my impulse, and I can use the other kind of the equation, the other part of the equation, F delta T. So let's say our impulse, 1560, and I forgot to mention, impulse, the units are a little bit different. Even though we're using changes in momentum, impulse is going to be Newton seconds, because when we talk about impulse, we refer to this part of the equation. So it's 1,560 Newton seconds. Okay, so we have Newton seconds there. Set that equal to force times change in time, which we're given right there. So that's our delta T. And now we divide both sides by 0.2, and we get a force of 7,800 newtons. And this will be a negative 7,800 newtons because that's the force that's working against the person. So now we want to take that force, and we can keep it positive if we want. We just want to figure out how massive an object could be that would generate that much force. So we want to use this force of 7,800 newtons and try to compare that to the mass of an object, just so we can kind of think about how large it might be. 7,800 newtons doesn't really, it's kind of hard to relate that to how massive an object could be or how much that force actually is. So we're going to use this equation here, force equals mass times gravity. So we'll use that 7,800 newtons and equal to a mass times gravity, which is 9.8 meters per second squared. So divide both sides by 9.8, and we get a mass of 795.92 kilograms. Now in the US, we don't know exactly how many 795.92 kilograms is, so we could take that times 2.2 to get what pounds would be, and that would be 1,751 pounds. So if we think about the car stopping, that would be comparable to an object that is 1,751 pounds being pushed against the person. And this is still mass, not the actual weight, but still mass and weight are somewhat connected. So that would be a quite massive object that would be compared to the stopping of that vehicle. All right, so now getting to the lesson here. So conservation of momentum, and we're starting off by just looking at our conservation of momentum problems again. So it applies in 2 dimensions. So last time we just talked 1-dimensional, and now we're going to talk 2-dimensional. So that would be maybe an object is going this way and an object is going this way. They crash and their resultant vector would look like that, because if they stuck together or something like that. Or we had maybe something at rest and it kind of gets struck on the bottom part, so then it's going to kind of veer off that way. So we have 2 dimensions involved here, which is going to introduce angles. Okay, so what we need to think about now is vectors. So the vector sum of the initial momentum equals the vector sum of the final momenta. So what we talk about with vectors would just be involving angles and directions. So we would have to consider velocities. So say we had mass times velocity. We had 2 objects. So let's say our second object here. We have to consider the angles involved here. So we may need to break these velocity vectors into components. And in order for this to work correctly, we have to have all the horizontal vectors together and all the vertical vectors together. So it'll make more sense when we look at an example. Okay, so then again, this is talking vectors here, so we have to have the initial components equal to the final components. So these would be the initial x components, the final must equal the initial, and the y components, the final must equal the initial. Okay, so when I talk about components, just to kind of review something, say we are on an xy plane and we have something that's going, I don't know, 15 meters per second at an angle of, let's just call it 45 degrees, because that's what it looks like. So remember, components, I have to take this 15 meters per second vector and break it into x components and then y components. So I would have an x component here that's going a certain speed horizontally and a y component that's going a certain speed vertically. Okay, so we'll have to break those apart. So just like an example I talked about when I drew it out, pool is a very good example for this stuff. So 2-dimensional collisions, and we do it kind of instinctively. You kind of try to analyze it in your head if you're trying to hit a ball and you're trying to get the 8 ball into one of the holes or something like that. But for example, we have ball D, okay, which is sitting at rest, and ball C was struck by some other ball, and it veers towards ball D. So we have an initial momentum here, right? So that vector right there represents our initial momentum. So this ball strikes that one right there, which is not head on, right? So that collision is going to cause an angle, or cause ball C to bounce off at an angle, which would be our final momentum there. So if we look at vector components here, so let's call this Cx final, and then we have this for ball D that has a momentum after it was struck, and then that one's going to have that x component, so let's call that D sub x final. If we put this vector with that vector, if we add them together, that should equal the x component, which is that vector, right? So these components, these are final components, must equal this initial component. Okay, so let's look at an example here. All right, so we have car C, which is 1,325 kilograms, moving north at 27 meters per second, and that car collides with a separate car, D, that is 2,165 kilograms, that's moving east at 11 meters per second. So this would be car C here and car D here. They're going to collide like this, and they're going to result in a velocity going off that after they stick together. So this would be a little bit more complicated if they're not sticking together, but not too bad. So for this one, we're just looking at the two cars collide and stick. Okay, so that would be called an inelastic collision. So what we have to do here is we're going to use our velocities here. So let's say we have car 1 right there. That would be car C, I suppose. That car is going north, and the other car, so car D, is going east. This one is going 27 meters per second, and this one is going 11 meters per second. They're going to collide, and it's going to result in some velocity or some vector like that. Okay, so now looking at these pieces that I've drawn here, what's kind of convenient when we work on these problems is these pieces are actually legs of this triangle here. So that's the 11 meters per second, and then that's the 27 meters per second. But the hypotenuse of this triangle is what would be our resultant velocity after the two cars collide. So most of these problems that we're going to do will work this way, is you'll have some kind of a northward velocity and some kind of an eastward velocity, and essentially those can be redrawn as a right triangle, like so, because remember, when you add two vectors together, you do tip to tail. And then this resultant vector is what we're going to be looking for when we're trying to find our resultant velocity. So let's redraw our triangle here, but now we're actually going to use values for momentum. So this would be momentum of car D down here, because that's the car going east, and this is going to be momentum of car C, because that's the one going north. And what we're looking for is that resultant momentum. So let's call that momentum sub R. Okay, so let's find these values off to the side. So we have car C that weighs, or that has a mass of 1,325 kilograms, and it's moving at 27 meters per second. Okay, and then car D, momentum for car D, that one is a lot more massive. It's 2,165 kilograms, and that car is moving slower, so 11.0 meters per second. So those momentums are going to be 35,775 kilograms times meters per second for car C, and car D is going to be 23,815 kilograms times meters per second. So let's put those values on our triangle over here. And so think about the way these kinds of triangles work. This is a right triangle because we made that with those vector components there. We had one going directly east and one going directly north, so I'd create a 90-degree triangle when I put them together. I can use Pythagorean's theorem to solve for that hypotenuse. So remember, Pythagorean's theorem is a squared plus b squared equals c squared. Now we're working with numbers that are a little bit bigger. Let's make this a little bit nicer. So since we're solving for c, we can just write out the equation for c. It's going to be the square root of a squared plus b squared. And then, so that's going to be my a squared, so 23, or that's going to be my a rather. I still have to square that, so these numbers are going to get pretty massive. And then b for my triangle is the 35,000. So I'm going to put this in my calculator, just using Pythagorean's theorem, and we end up getting 42,976.79, and that's a momentum quantity, so that's kilograms times meters per second. That is the hypotenuse of this triangle, so 42,976.79. So that's the resulting momentum after the collision. Okay, so now we want to use that. We can use that value to figure out the direction and speed the cars move after the collision. All right, so The easy one to take care of is the direction, okay? Because we're just looking for this angle, and we have this quantity and this quantity that we can use to find angle theta here. So what trig function are we going to use? Well, we have an opposite leg and an adjacent leg, so that means we're going to be using tangent. So we use tangent of theta, and we set that equal to, remember, it's opposite over adjacent, so that would be 35,775 for that momentum divided by 23,815. And then we're looking for theta. So remember what we're going to have to do in order to find this angle. We're going to have to use inverse trig functions of both sides. So that'll take care of that, and we're left with theta. So we can do inverse tangent of 35,775 divided by 23,815 to get that angle. So make sure that your calculator is in degrees and not radians here. So that inverse tangent is going to give us an angle of 56.35 degrees. Okay, and then we can give some directions to that, because we have to have more than just 56.35 degrees. This would have to be north of east. So we have to give directions to that angle, so we know which specific direction we're looking. So for the second part of this here, which should be a little bit more difficult, we're trying to find the final speed of that system after they've collided and stuck together. So final momentum, we said it was 42,976.79. Okay, now we have to think of what we need to do with this. So this is momentum equals mass times velocity. So we have that 42,000. So what we have for the masses now, since they stuck together, we're going to have the mass of car C and the mass of car D times that final velocity, since those stuck together. So we want to input those values for the masses. So we have 1325 kilograms plus 2165 kilograms times that final velocity. And we can just divide both sides by those masses. And when we do that, we get a final velocity of 12.3 meters per second. So after they run into each other and crash and stick together, the system will be going 12.3 meters per second at an angle of 56.35 degrees north of east. So you can see that these problems can take quite a bit of work. So we had to find initial momentum of the system, so we could find the final momentum of the collision by using vector quantities, because this is my horizontal vector quantity and this is my vertical vector quantity, and those are initial. So then my final, this one, must be the same as what these two were before the crash. Okay, so let's try another one of these. So same kind of idea here, just the numbers are a little bit different. So maybe you want to pause the video and try it before we work through it. But we have some directions that are a little bit different. So I'm going to start by drawing my vectors here. So we have car C moving south at 22.5 meters per second, and then the other car is going west. Okay. So west at 17.5 meters per second, they collide, and it results in a vector that's going down this direction. So this is the angle that we're looking for, because they're colliding and they're going down that way, as shown in this vector right there. So let's find our momentum quantities here. So we have momentum for car C again, and then we have momentum for car D. So this is just going to be mass times velocity. So the velocity is 22.5 meters per second. And then for car D is 2165 kilograms times 17.5 meters per second. All right, so car C is the one that's going south, and car D is the one that's going west. So car C, I'm just going to put it on a triangle right away here, has a momentum of 21,937. 37,887.5, and car D has a momentum of 37,887.5. And again, we're going to do Pythagorean's theorem here. So it's going to be C equals square root of 21,937.5 squared plus 37,887.5 squared. So that's just a squared plus b squared equals c squared. And since we are going with c, we had to square root the equation. And we end up getting a momentum of 43,780.3 kilograms times meters per second. So that's the momentum of the system here. So 43,780.3 kilograms times meters per second. So in what direction relative to south, and with what speed do they move after the collision? So this would be my southern vector there. So we're looking at this angle right there. And again, just like we did up above, we're going to use tangent. So tangent of theta. So that's going to be opposite over adjacent. So it's going to be the 37,887.5 over 21,937.5. And then we'll have to use inverse tangent to get rid of the tangent. And that gives us an angle of 59.9 degrees. And then since this is the angle right there, that angle is west of south. So we will say west of south. And then we need to find the speed of the system. So remember, we're going to use our final momentum here. And we set that equal to the mass of the system now, which is both vehicles together, times its final velocity. So we'll divide this quantity out from that value, and we get a final velocity of 13.9 meters per second. So we have the system is now going 13.9 meters per second at 59.9 degrees west of south. So once you've done one of these problems, it's pretty simple to do another one just like that. Although if they collide together and then bounce apart in a perfectly elastic collision, then you would have to do the final velocities of each of the cars, and you have to know what direction they're going after that. All right, so let's take a look at angular momentum here. The conservation laws also apply to angular momentum. So law of conservation of angular momentum states that if no external forces or torques act on an object, then the angular momentum does not change. So just like our linear momentum, this is final angular momentum is equal to initial angular momentum. So that's the law of conservation of momentum for angular scenarios. And if you forgot, so angular momentum is written with an L, and that is the moment of inertia times its angular velocity. So a lot of the times we need to figure out this in order to find that, okay? Or we're trying to look and see how this changes if I have a change in my moment of inertia. So take this ballerina over here, for example. Their moment of inertia is different here compared to this one, because remember when we talked about this, or when you've heard about this scenario, when the person puts their arms out like that, essentially it's increasing the radius from their center of mass. So you're getting mass out there, we have mass all the way out there, right? So then the other arm's there. So increasing the radius is going to do a lot of things. It's going to increase the drag, slow the person down, increase the moment of inertia. But if we disregarded air resistance and drag, the main thing that's going to happen is that moment of inertia is going to be bigger here because the mass is further from the center. And then as soon as that skater or that ballerina brings their arms in, like the second picture there, they're effectively reducing their radius, which makes their moment of inertia a lot smaller compared to this one. Okay, the drag is reduced, moment of inertia is reduced, or the inertia is reduced just because the mass is much closer the general mass is much closer to that center of mass. So that's how they can spin much faster, and then maybe at the end of the spin they put their arms out again to slow down. But our momentum for this scenario will equal the momentum for this scenario, or vice versa, depending on which one we're considering to be the final or the initial. Okay, so let's check out a problem. So a merry-go-round at a playground, okay, is rotating at 4 revolutions per minute. 3 children jump on and increase the moment of inertia. So we got our 3 kids here, they're jumping on here, and it increases the moment of inertia by 25%. So what is the new rotation rate? That's what we're looking to find here. So let's write out our equations. So final momentum equals initial momentum. And now we're not really given a moment of inertia. We're not really given a value for I. So if you're not given something like that, then, and we have we're just saying it increases by 25%, then let's just say our initial moment of inertia is going to be 1. Okay, so that'd be 1 kilogram times meters squared. And we made our lives quite a bit easier by just saying that that's 1, because we know that it increased by 25%, so then we can say the final moment of inertia is going to be 1 1/4 or 1.25, because it increased by 25%. So 25% would be 0.25, so I'm adding 0.25 to it. So I have 1.25 kilograms times meters squared for my final moment of inertia. And then we do have an initial angular velocity of 4 revolutions per minute. And we can actually just leave that in revolutions per minute because it doesn't specify what we want to find our final answer in. So we have enough information here to find. We're looking for this. We don't know our final angular velocity. So let's start throwing some things in here. So our final moment, this one's going to be final moment times final angular velocity equals initial moment times initial angular velocity. So we have our final moment of 1.25. Final velocity we don't know. Our initial moment is just 1. That makes it a lot nicer. And 4.0 revolutions per minute. Okay, so this turns out being some fairly simple math here because we're looking for that. So we just divide both sides by 1.25. And we're going to get a final angular velocity of 3.2 revolutions per minute. Okay, so that's the general idea when we're working with angular conservation of momentum. We need an initial and final moment of inertia, and we need an initial and final or angular velocity. Okay, so in the grand scheme of things, this is a fairly simple idea because there could be a lot more variables involved here, which could complicate our moment of inertia. If we have more things getting involved, then we'd have to find the moment of each item involved when they combine together. So the last idea, just to kind of hit on, so since we're talking about rotational momentum and inertia and things like that, tops and gyroscopes come out quite a bit. So when a top is vertical, there's no net torque on it, and the direction of rotation doesn't change. So think about if this top were just kind of sitting vertical like that. Okay, so the center of mass is vertical as I can draw it here. The thing is rotating, and it's just going to keep spinning like that. Right? If there were no outside forces involved, no drag, no friction, then that's just going to keep spinning like that forever. And we could calculate, if we wanted to stop that, and we could calculate initial and final momentum in the scenario. But as soon as this starts to tip, so we have this thing called gravity, as soon as this top starts to tip a little bit, then it starts to look like this scenario here. So what's going to happen is gravity is going to be pulling down on the center of mass right there. And that's going to cause that top to then spin around an axis. Okay, so that's called the precession of the top due to torque, which is caused by gravity. Okay, so if you haven't seen a top do this, then I would suggest going to YouTube and watching a video. But as soon as the top starts to veer a little bit, so let's just kind of draw a basic top. As soon as that top starts to veer a little bit from its axis, say it turns a little bit like that, then that axis, it just keeps getting larger and larger because more and more torque is pulling down on that from gravity. But what's kind of interesting here is that that center of mass is rotating around a central axis still. So it kind of maintains that axis right about that point. There's that point of rotation, but that is the precession of the top. So if you wanted to see this behavior of objects in rotation, you could just take a coin, take a quarter, something like that, and you could take the quarter and initially give it some angular velocity right there, and then once it starts to slow down, this point here starts to kind of tip a little bit, and then it begins to tip like that, and then after a while, then it's just kind of flopping around on the ground here a little bit because eventually that torque is bringing it down. But for a moment, that's going to spin around that rotational axis. Another similar idea to talk about is the idea of a gyroscope. So right here is a gyroscope, and what is happening here is we have a wheel that is fixed on a central axis right there, and there could be multiple wheels on here, but here we just have one. So this wheel right here is creating a rotational momentum. So this wheel is spinning, creating that momentum, and that rotation there is actually causing a force. So we have centripetal acceleration involved here. That mass is going around like that, but there's a torque involved here, and we follow the rotation of that axis, or of that wheel there. Let's say that wheel is spinning around this way, and we have this thing called the right hand rule. So if I took my right hand and wrapped it around that wheel there, wrapped it around that axis there, that would show me that I have a force generated that's going in this direction. Okay, and it would also work the other way. But that force in the upward direction or straight downward direction is going to want to keep that gyroscope from moving around. So it's going to have, if you spin it really fast, it's going to maintain that vertical position for a while, but then as we just talked about in the last slide, it's going to start to tip a little bit in this example, and you can kind of see it spinning around that central axis as it starts to lose a little bit of that momentum. So I'll have other videos linked to this assignment, and I'll have other videos in the description if you want to check out how a gyroscope works. It's pretty amazing, pretty simple toy, can be fairly amazing in the world of physics. And over here I have another GIF of a gyroscope. So this is a little more extreme, but you can see that there's more rotation going on, and this would be if you put this up on that pedestal. After a while, it would start to slow down and it would exhibit this kind of behavior here, because it still is generating that rotational momentum or that torque, and it wants to push outward. So that force pushing outward is going to keep that from falling down. So after a while it would fall down due to drag and gravity and such, but it's kind of cool how it stays up and just keeps rotating around like that. Okay, so this concludes our lesson on conservation of momentum and rotational conservation of momentum. So if you wanted to check out more of these ideas, I'll have links in the description below. And thanks for watching.